Hello, I'm Kobayashi from Sony. Today, I will be discussing what can be done with deep learning and answering the question of what specifically deep learning can be used for. Deep learning became famous through image recognition, so there are probably many people who view it as something used to achieve image technology, recognition technology, or some sort of intelligent technology. However, deep learning is a technology with an extremely broad range of application. You could say that deep learning is a general-purpose technology. It's a technology that can help achieve a truly diverse range of functions depending on how it's used. This chart shows that many functions can be achieved through a variety of changes to the input and output of the neural network. For typical image recognition, the input is an image and the output is the result of image classification. In other words, the output indicates the type of image. This means that it functions as image recognition if the neural network is used. For example, if an image input for image recognition is converted to text, it will function as automatic text classification. If the neural network is trained to output the type of text that was input, we have a model for classification of text rather than for image classification. Using the same concept, if the input is speech waveform recorded with a microphone rather than images or text, the output can be a text. Configuring the neural network in this manner allows it to function as speech recognition. A truly wide variety of functions can be achieved by changing input and output in this way. This general versatility is one of the main reasons that deep learning is called a disruptive technology. Now I will explain the ability to achieve a variety of applications by changing input and output with some examples that are a bit more concrete. First is an example of application to images. The first example of application I will introduce is object detection. This is already a very typical application of deep learning. Object detection can be achieved simply by developing the image classification we discussed a bit more. In the case of the object classification just mentioned, the input was an image. It is the same here. The output a moment ago was the object category, but in the case of object detection, the output is information such as the position, type, and size of multiple objects included in the input image. This type of object detection function can be achieved by using deep learning to train the neural network to output the type and position of objects from an input image. It's also possible to recognize the object type down to the pixel level. In computer vision terminology, this type is called semantic segmentation. Images are input with the neural network to achieve semantic segmentation. This is the same as previous examples, but the output is the category of each pixel of the input image. If training can be conducted with data indicating the type of object of each pixel in an output image, it becomes possible to create an image classifier that provides highly detailed classification results in this manner. It is also possible to output an image that corresponds to the input image itself. In this way of thinking, deep learning can be used to achieve image signal processing or image conversion functions. A typical example would be training the neural network to output a high-resolution image from a low-resolution input image. This would make it possible to create a super-resolution algorithm to improve the resolution of images. Using the same concept, noise can also be removed from images. A noiseless image can be output from an image that has noise. Color can be added to monochrome images. In other words, monochrome input images can be output as color images. Other proposed applications include algorithms to change the style of images. Up to this point, the examples have used a single input image, but there is no particular need to limit it to just one. For example, it's possible to create an image similarity determination model that can determine whether two input facial images are pictures of the same person. This type of similarity determination model could be used as a facial verification software to determine whether the image of a face taken with a camera is of the same person as the person in a facial image registered in advance. Next, I will discuss examples of application to language. One example of great success in applying deep learning to language is machine translation. For example, if the input is a string of Japanese text and the output is a text of English words, training the neural network with a large amount of translation pair data makes it possible to train a model for translation from Japanese to English. This type of machine translation model created using deep learning is known for providing an extremely high level of performance compared to the conventional method that utilizes text structure analysis. Something like a chatbot can be created using the same mechanism. In such cases, the input is the user's input text message, and the output is a text for the response expected of the chatbot. Using a dataset consisting of this input and output to train the neural network makes it possible to create a chatbot that returns a suitable response. The relationship between this input and output does not have to be between images or between text. For example, having an image as the input and a text as the output is possible. Applying this configuration makes it possible to achieve a function called image captioning, for example. Image captioning achieves a function to output a text explanation of an input image. A combination of images and text can be set as the input and output as well. For example, in the case of application for visual question answering, a combination of images and text is taken in as the input. Here, the text is a question about the image. The output from the neural network is the answer to the question about the image. For example, in the case of this photo of 3 children, if the number of children in the photo is input, the neural network responds with 3. In this way, it's possible to achieve a function for responding to questions about an image. Finally, I will also discuss examples of application to things other than images and language. One simple example of application to something other than images and language is the problem of handling input vectors. This means using deep learning to solve identification and recovery problems that have been conducted using conventional machine learning in the past. For example, in the case of the real estate price estimate engine used by SRE Holdings, the neural network is trained to output real estate prices, which is a continuous value, indicating that the price is so many tens of millions of yen from input feature quality vectors, which are the various types of real estate information. A real estate price estimate engine achieved in this manner makes it possible to estimate the rough assessed price of real estate that is not for sale, for example. This is an example of application using chronological sensor information as the input. This Xperia ear headset contains sensors that make it possible to track the movement of the user's head. Head gestures such as nodding to indicate yes and shaking the head to indicate no are recognized based on this sensor data. Configuring the neural network in this manner makes it possible to achieve a gesture recognition function based on chronological sensor information. Deep learning can also be used to detect abnormalities in data. When creating this type of function, we design the neural network to output the degree of abnormality in the input data. Abnormality detection can be used for things such as predicting malfunctions in manufacturing equipment in factories, for example, by configuring it to calculate the degree of abnormality based on data from sensors installed in the equipment. Deep learning can also be used to control robots. For example, the neural network can learn a control algorithm for controlling the robot to function properly and achieve a purpose based on the situation. This is done by training the neural network using signals from sensors in the robots as the input and information such as the torque of servo motors or other controlled variable actuators that determine how robots will be operated as the output. In this way, we can create a control algorithm to control the robot so that it functions properly based on the environment. Let's tie this all together now. As we have seen, deep learning is an extremely versatile technology that makes it possible to achieve a variety of functions by changing input and output in various ways. In this tutorial, we have discussed what can be done with deep learning, but the question of what can be done with deep learning is similar to the question of what can be done with software. As you know, software is currently being used to provide a variety of functions that are all around us. Deep learning is a versatile technology that can be used to achieve various functions at the same level or even higher. In short, the examples of application discussed today are merely a small sample. How can deep learning be used to create output and from what type of input? What kind of function for this will please the customer? How can deep learning be used to improve work efficiency and quality? Asking questions such as this without getting stuck in the rut of application to images or other existing applications and considering the key points of utilization from this perspective is certain to result in an expansion of new applications. I also believe that discovering the key points of utilization that are close to the issues you deal with in your actual work will be the first step in utilizing deep learning. I look forward to the new ways of utilizing deep learning that you discover by thinking outside the box.